So I wrote these two equations on the board just so you guys could so I could show them to you. Well, again, to really make sure everyone is very, very familiar with the formulas for calculating both the moments and the mass, so you can find the center of mass, which is also the centroid. And again, the only difference between center of mass and the centroid is in the centroid, you get to assume that the density of the object is 1 or constant everywhere. So that when you do this division, the density here and the density here, when you divide these, since they're constants, they can come out in front and cancel out. So when you're finding the centroid, you're really just finding the physical center of an object. When you're finding the center of mass, you're finding the balancing point, right? Because maybe it's heavier on one side than the other, which wouldn't be like if a circle was heavier on the left side than on the right side, or sorry, the right side than the left side, right? In a circle, you have a circle. A good pen. I have a good pen somewhere. The pens are hiding from me. Oh, there's a good pen. Sorry, right? If you had a circle that was heavier on the right side than the left side, the center of mass would be somewhere over here because there's more weight on that side. But the centroid of a circle is just the center. It's the geometric center of the object, where there's as much area on one side as the other, no matter where you cut it. So, right, cutting it here, cutting it there, cutting it there, is always cutting the circle geometrically in half, whereas the weight would not be equally distributed on either side. So, yeah, let's go ahead and talk. So here are the formulas for mass. So again, the mass of a region with some density is just the integral of the density times the area of the rectangle. And the area of the rectangle is the top function. Oops, oh, I made a small mistake. Let me just relabel things here real quick. I did make a small error. I accidentally called this G and this F. Apologies. This bottom function is the G function, and this top function is the F function. Sorry about that. So let me uncover I have the chat covered up, which is always a mistake. Be able to see the chat. There we go. Cool. Okay, so the area of the rectangle is just the height, which is F minus G, times the thickness, which is dx. So that's how you find the mass. And then the moment around the x-axis, around the y-axis, is just the mass of the rectangle times the distance to the y-axis, or the lever arm. So the distance to the y-axis is just x. So we're doing x times, again, that same density times area, which is f of x minus g of x times dx. And then the moment around the x-axis is the same idea. The moment around the x-axis is, again, the distance to the x-axis times the mass of the rectangle. The mass of the rectangle hasn't changed. It's still density times f minus g times dx. But the distance to the x-axis is a little bit harder to deal with because this whole shape isn't the same distance. So we imagine that all the mass of that rectangle is at the center of mass of the rectangle. And then we say, okay, how far is that from the axis of rotation? And that is the average of this f and g function, which is 1/2 f plus g. So we end up getting that the moment around the x-axis is, again, the integral of the distance to the x-axis, which is 1/2 f plus g, times the density times f minus g times dx. And then we usually simplify this equation. We bring out the 1/2, and f plus g times f minus g is f squared minus g squared. And then we have the density right there. So this is the formula for going around the x-axis, the moment around the x-axis. And then finally, to find the centroid, x bar and y bar, or the center of mass, x bar, y bar, it's just the moment around the y-axis divided by the mass, and then the y-coordinate is the moment around the x-axis divided by the mass. And then we have all these formulas in terms of y as well. So if I had the same sort of shape, but I was using a horizontal rectangle instead of a vertical rectangle, then, and I would do this, especially if the density was in terms of y, then my moment around the, my mass would still be the same sort of calculation, is still be the integral of the density times the area of the rectangle, which is its length, which is h minus k, times its thickness, which is dy. The moment around the x-axis, if this strip is y away from the x-axis, the moment around the x-axis is the integral of the distance to the x-axis, or the distance of the lever arm, times the density times the area. And then the same is true for the moment around the y-axis. We're going to say it's still the integral of the distance of the or the length of the lever arm times the area times the density. But here, the length of the lever arm, like in the other one, right? Say, oh, well, this whole thing isn't all the same distance from the y-axis. So we imagine it all centered right there. And we say that point is, how far is it from the y-axis? It's half of the average. It is the average of the function values, 1/2 h plus k. So we get the same sort of formula where you get 1/2 times the density times h squared minus k squared. And it should be from C to D. These are the various formulas for center of mass, for I should say for mass, for moments, and then the center of mass is just the moments divided by the mass. And it is always that x bar is equal to the moment around the y-axis divided by the mass, and y bar, the y coordinate, is the moment around the x-axis divided by the mass. Before we do an example, are there any specific questions about these equations?
On the other side of the board, it was to find mass, it was density times the area of
the rectangle.
Oh, the rectangle?
Right. This rectangle here in red, the area is the base, which is dx, times the height, which is f minus g, which is exactly what we have right here. Dx times f minus g. Other questions? Okay, let's do a couple. I know we did some last time. I think it's still worth practicing a little bit more. Let's do a couple more problems. So, all right, we'll do this, sure. So I want to find, we'll do the calculus. So let's find the centroid, meaning we're just going to assume the density is 1, of the region bounded by y equals x squared and y equals, let's make it not too terrible. Y equals 2x. Yeah, let's find that. So I'm going to graph it. We don't have to graph it. We can totally see where those intersect. Y equals x squared looks like this. Y equals 2x looks like this. They definitely intersect at 0, 0. And we can set them equal to each other. X squared equals 2x. X squared minus 2x equals 0. X times x minus 2 equals 0. So x is going to be 2. Y is going to be 4. So again, I'm going to make the assumption the density is equal to 1. Uniformly dense, no matter what x or y is. So then when I find the mass, I'm really just finding the area, right? Because it's the right, the mass is the density times the area. The density is 1, so the area and the mass are going to be the same. So that's going to be the integral from 0 to 2 of the top function minus the bottom function. Right, that's the area of my rectangle. And the density, which I didn't write, is 1. Okay, so integral of 2x is x squared, integral of x squared is x cubed over 3. From 0 to 2, we get 4 minus 8 thirds. 12 thirds minus 8 thirds is 4 thirds. Great, there's my mass of my region, my area of my region. The moment around the y-axis. So again, it's the integral, it's the same integral of your mass of your rectangle or area of your rectangle, since the density is 1. But we actually have to throw in the distance from your strip to the axis you're rotating around. Okay, that's our lever arm. The further away from the axis that the rectangle is, the more moment you're going to get, because you're going to be more likely to swing. Because, right, if you ever tried like opening a door or a window, right? If you like, I mean, I'm sure you've all opened doors or windows, but if you've ever like tried to be silly and like push the door from like the inner corner, like right near the hinge, it takes a lot more effort to push it there, because the moment, right, there's so much more, you need more, trying to think about the right word is here. But basically, right, the tendency of like this part wants to, you can exert a lot less force, because the lever arm kind of acts at, it amplifies your force, right? Pushing here does a lot more than pushing here with the same amount of force. I know this is like a flimsy piece of paper, so it doesn't matter. Right? If you actually push on the door, right, it's much easier to push or pull it from the outer corner than from the inner corner, because of that magnifying effect of the lever arm. The lever arm gives you more moment. The longer the lever arm gives you more moment. Calculating this, it's going to be the integral from 0 to 2 of 2x squared minus x cubed dx, which is going to be 2x cubed over 3 minus x to the 4th over 4 from 0 to 2. It's going to be 8 over 3 minus, sorry, not 8, 16 over 3 minus 16 over 4. This is where I would factor out a 16 and say it's 16 times a third minus a fourth. 4/12 minus 3/12 is 1/12. So this is 16 times 1/12, which is going to be 16/12, which reduces to 4/3. That is a coincidence that the mass and the moment happen to be the same. Interesting. Let's find the moment around the y-axis. Sorry, the moment around the x-axis. I want to find the moment around the x-axis. I can either use the alternate formula, which is probably the one we should use, right? We could solve for things in terms of y, but we don't have to. So the moment around the x-axis, it's going to be the integral of 1/2 of f plus g, so the top thing plus the bottom thing, so 1/2 of 2x plus x squared, right? That's my lever arm, times, again, the same area of my rectangle, which is just 2x minus x squared. Really want to make sure everyone's super cool with that, right? So then, oh, and still from 0 to 2. Factor out the 1/2. And then if we multiply this out, we get 2x times 2x, which is 4x squared. You're going to get minus 2x cubed plus 2x cubed, which cancels out. And then you're going to get plus x squared times minus x squared, which is minus x to the 4th. So I really want to point out, this is 1/2 times the top thing squared, 2x quantity squared, minus the bottom thing squared, x squared quantity squared. Sure, of course. Yeah, totally cool. And then we integrate this. We get 1/2 4x cubed over 3 minus x to the 5th over 5 from 0 to 2. Plugging in 2, we're going to get 1/2 times, let's see, 4 times 8 is 32 thirds minus 32 fifths. And we are going to, that's a 3, right? I can factor out a 32 here like I would. So 32 over 2 is 16, and then 1/3 minus 1/5, that's 5/15 minus 3/15, which is 2/15. So that's 16 times 2/15, which is 32/15. All right, and then we have to find, well, we have to really have to write down what x bar and y bar are. So do I have any room? I guess I have some room I can carve out right here. Let me do it in red. So x bar, y bar, the coordinates of the centroid or center of mass, this is the centroid, is my over m, comma, mx over m. Which is going to be, see, so my was 4/3 divided by the mass. So that's going to be 4/3 over 4/3, which is 1. And then the y coordinate is going to be mx, 32/15 divided by 4/3 is like multiplying by 3/4. So that's going to reduce to, let's see, 32 over 4 is 8, 3 over 15 is 1/5. So that's going to be 8/5. So 1, 8/5 is my center of mass. So literally halfway between here and 8/5, right? So let's see, that's 4, 2, 1. 8/5 is like 1 3/5, so like maybe like right up there. So there's approximately where my center of mass is. Couple things we could do now if you wanted to. So yeah, let's not do it quite yet. And I should say that's the centroid in addition to being the center of mass, right? It's the centroid because we assume the density was 1. What if the density wasn't 1? What if the density at, say, a height of y, the density of your thin plate was, I don't know, y plus 1? I feel like that's going to be terrible. Y plus 1 is good. Let's just say y. Let's not make our things too complicated here. Well, it's going to make things more complicated because, one, we now have to do things in terms of y. So our region, let's look like this. It's still the same region, but now we have to use horizontal strip. So our mass, well, actually our mass has changed, right? Because now we have a variable density. So let's find all the things again. So the mass is going to be the integral of the area of this strip times the density of the strip. So the area of that strip is, let's write down the functions. And this is y equals x squared. This is y equals 2x. Y equals x squared is going to be x equal to the square root of y. And y equals 2x is going to be x equal to 1/2 y. So the area of that rectangle is the right function minus the left function. So that's going to be square root of y minus 1/2 y times dy. That's the area of that rectangle times the density of the rectangle, which is y. From as low as 0 to as high as 4. All right, things are looking messy already. So this is going to be the integral from 0 to 4 of y to the 3/2 minus 1/2 y squared dy. We're going to integrate. And we're going to get, let's see, 2/5 y to the 5/2 minus 1/6 y cubed from 0 to 4. It's looking real great. I mean, it's actually not as bad as it looks. So when you plug in 4 to the 5/2, the square root of 4 is 2, 2 to the 5th is 32, 32 times 2 is 64. So you get 64/5 minus 4 cubed is 64, so you get 64/6. Factor out of 64. 1/5 minus 1/6 is 6/30 minus 5/30, which is 1/30. So you get 64 over 30, which reduces to 32 over 15. That's the mass of the shape with this variable density of y. To find the moment, let's do the moment around the x-axis first. Because the moment around the x-axis, all of this is the same distance from the x-axis of y. So the moment around the x-axis is going to be the integral, still from 0 to 4, of y, which is my lever arm, times all of that mass of that rectangle. So that's going to be times another y times y to the 1/2 minus 1/2 y. Okay, so again, right, these moments are usually not nice to calculate. This is going to be, let's see, so if I multiply this out, I just have another factor of y. So instead of having y to the 3/2 minus 1/2 y squared, I'm going to have the integral of y to the 5/2 minus 1/2 y cubed. And when I integrate that, I'm going to get 2/7 y to the 7/2 minus y to the 4th over 2 times 4, which is 8. From 0 to 4. Okay, things are getting dicey. 4 to the 7/2 is the square root of 4, which is 2 to the 7th power, which is 128. So you have 2 times 128, which is 256 divided by 7. And then 4 to the 4th power is 2 to the 8th power, which is 256 divided by 8. Once again, factor out the number, and you get 256 times 1/7 minus 1/8, which is 856 minus 756, which is 156. You can cancel a 4 from each of those, so this reduces down to 64, and 56 divided by 4 is going to be, I think we can cancel an 8, sorry, more than a 4, you can cancel an 8. 56 divided by 8 is 7. This reduces to 32/7. Okay, now I have to calculate my, which is always, so I will say, if your integral is in term, if your stuff's in terms of y, calculating the moment around the y-axis is the hard one. Just like here, if things are in terms of x, going around the x-axis, that moment is the more difficult calculation. Let's do it. I don't want to erase the other side just yet, so I'm going to have to erase something here. I guess I can erase the mass. It was 32/15. Just write that down over here. Okay. So let's see here. The moment around the y-axis is going to be, again, the integral of the lever arm. In this case, the lever arm is going to have to be the average of the two functions. So it's going to be 1/2 the right function plus the left function. So that's going to be 1/2 y to the 1/2 plus 1/2 y times the mass of the rectangle, which is going to be y times y to the 1/2 minus 1/2 y. Okay, so I'm pretty gnarly. So that's going to be 1/2 integral from 0 to 4. So when I multiply this out, I get y to the 1/2 times y to the 1/2, which is, I'm going to bring actually that y first. So that y is right there. Y to the 1/2 times y to the 1/2 is y. And middle terms cancel out. And you get minus 1/2 y times 1/2 y, which is 1/4 y squared. It's not so bad. Let's just multiply the y and get 1/2 the integral from 0 to 4 of y squared minus 1/4 y cubed. Whew. So then we're going to get 1/2 y to the 3rd over 3 minus y to the 4th over 16 from 0 to 4. So we're going to get 1/2 64/3 minus 4 to the 4th over 16 is 4 times 4 times 4 times 4 over 16. And I'm only going to cancel 2 of those, even though I could cancel 3 of them. I'm sorry, I'm only going to cancel 1 of them. So that's that. So I've got 1/2 of 64/3 minus 64/4. Well, I can factor out the 64. And you get 64 over 2, which is 32, times 1/3 minus 1/4, which is 4/12 minus 3/12, 1/12. And you can factor a 4 here, cancel a 4 here and 4 here, and get 8/3. Okay, so now finally we can say that the x bar coordinate is my over the mass, which is 8/3 divided by 32/15, which is 8/3 times 15/32. 8 over 32 gives me a 4, 15 over 3 gives me a 5. So that's 5/4. And the y bar coordinate is mx divided by the mass, which is 32/7 divided by 32/15, which is just going to be 15 over 7. Because the 32 stands in. So the center of mass, when the plate gets heavier as you go higher, interesting. Sorry, I'm just curious about something. Sorry, anyway, is going to be, where'd you get here? Sorry about that. Oh, it's going to be right. So over, the x bar coordinates like 5/4, which is a little bit more than 1, and the y bar coordinates 15/7, which is a little bit more than 2. So somewhere like there. Right there. Because again, right, it's heavier as you move further.
Question for the mass to the y.
Yeah. For my here.
My.
Yeah.
How did you get the second line? 1/2.
Sure. So right, this quantity here times this quantity here, it's just a difference of squares factored out. I have a plus b times a minus b is a squared minus b squared. So that's y to the 1/2 plus 1/2 y times y to the 1/2 minus 1/2 y. So I'm getting y to the 1/2 squared, which is just y, minus 1/2 y quantity squared, which is 1/4 y squared.
Oh, so you just multiplied it. Oh, okay.
And then I multiplied the y through to get y squared minus 1/4 y.
Yeah, okay. Yeah, that was my question. Thank you.
You're welcome. Something my brain is having trouble wrapping its head around, but that's all right. Oh yeah, that makes sense. Okay. Sure. Other questions about this?
Yeah, James, I have a quick question. I get the whole thing, and just the only thing I don't get is how, how we did like horizontal lines and then we saw for y and stuff like that. So pretty much like for this one, we went horizontally. So we would have to do on the m of y, we would have to do 1/2 parentheses y 1/2 plus 1/2 y. And if it was the other one, when we did a vertical line, it will be for mx, right?
Right.
Okay, for sure.
So the reason we had to do this one using y was because we had density as a function of y.
Yeah.
Whereas this one here, since the density was constant, if we had wanted to, we could have found mx using an alternate formula. We could have found, but let's go ahead and do it. We could have found mx here using a horizontal strip and said, okay, mx is the integral of the lever arm. The lever arm is just y times the length of the, or the area of the strip. And the area of the strip is the right function, which is square root of y, minus the left function, which is 1/2 y, dy from 0 to 4. So this is going to end up, I think, which actually I think we already did. I erased it. So anyway, We did this in a different context. Let's do it again. That's going to be the integral from 0 to 4 of y to the 3/2 minus 1/2 y squared dy, which ends up being y to the 5/2 times 2/5 minus y to the 3rd over 6 from 0 to 4, which ends up being 64/5 minus 64/6, which ends up being 64/30, which is 32/15. 32/15. So they're the same. So I'm not saying you should do this, but what I'm saying is if you're just being asked to find a centroid where the mass is not, where the density is not variable, you can use both, and you can, and it's possible to solve both for y as a function of x and x as a function of y. If you really wanted to, you could use both of the quote unquote easier moment formulas.
Also, it's pretty much your preference, like the
if it's this, well, then you have to meet some very specific conditions. It's your preference if you're doing a centroid, right, and the mass is not variable.
Okay, yeah. Okay, yeah.
Here we didn't have a choice. We had to do it in terms of y because the mass density was variable. But you also have to be able to solve for y as a function of x and x as a function of y if you want to do it either way. And there are some things you couldn't, like for example, if my region were this, the region bounded by y equals x minus x cubed and y equals 0 in the quadrant, in the first quadrant. So my intercepts are 0 and 1. There's also an intercept at -1. I don't care about that. It looks kind of like this. If I want to find the moment of this, I have to do things in terms of x. Not because the density is variable, but because I can't solve for x as a function of y. So I couldn't use a horizontal strip even if I wanted to.
Yeah, it would make sense. That would, yeah.
Right. Most of the time what we do is we just use the functions the way they're given to us.
Okay.
Unless there is something preventing us from doing that, like the problem I just erased here, where
of course
functions in terms of x, we need to do it in terms of y.
Of course. Okay, yeah, I get it. Thank you so much, James.
You're welcome. The other thing I want to say about this is we could then use our centroid, which is 1,8/5, to find the volume of this region to find the volume of the solid generator that revolve in this region around any kind of axis you like. So for example, if I wanted to revolve this around the y-axis, the x-axis, well, remembering that the area of that region is 4/3, the volume you get when you revolve this around the x-axis is just the 2 pi times some length here times the area. And that length is the distance from the centroid to the axis of rotation. This is Pappus's theorem. So for example, this one here, if I was going around the x-axis, right, the distance from the centroid to the x-axis, well, that's just the y-coordinate, which is going to be 8/5. So if I revolve this around the x-axis, the volume around the x-axis is going to be 2 pi times 8/5 times the area, which is 4/3. Done. Instead of having to do the shell method or the washer method, right? Whereas with washer method, so I should say, if the centroid is easy to find, it's not easy to find too. If the centroid generally is easy to find, using Pappus's theorem is really powerful. Or if you've already found the centroid, using Pappus's theorem is really powerful. So if someone's already asking you to find the centroid and then asking you to find the volume, as well, like, obviously Pappus's theorem. So if I want to find the volume around, say, like the line, I don't know, y equals 5. Let's do x equals something. That's more interesting. Around the line, say like x equal to -3, it would just be, again, the same formula. 2 pi times the distance from x equals -3 to the centroid. Well, the x coordinate of the centroid is 1. The difference between 1 and -3 is 4 times the area. That's it. That's Pappus's theorem in a nutshell. Actually, there's a little bit more to say about Pappus's theorem, which I'll say in a moment. Yeah. Okay. Yeah. So there's a couple homework problems that have to do with Pappus's theorem. One of them is the following, or similar to the following. I'm gonna make a different one. So I'm gonna make one. Let's do a triangle. A triangle with coordinates, with vertices. Let's say, I don't know, 0, 2, 6, 2, and 3, 4. What's the volume you get of the solid if we rotate the triangle about, let's do two things. Let's do the line x equals 8, and let's do the line y equals 0, which is the x-axis. Okay, so let's draw a picture. So let's see here. I've got the point 0, 2, 6, 2, and 3, 4. Okay. Clearly, this triangle is isosceles, right? The distance from here to here is 6, and the distance from here to here is 3. So we know that the centroid is somewhere on this line. Maybe it's about right there. But here's the thing. If we're going around the line x equals 8, no matter how high the centroid is, the distance from the centroid to our axis of rotation is just 5. So the volume you get when you revolve this around the line, x equals 8, is going to be 2 pi times the distance from the center to the line, which is 5, times the area of this rectangle, which is 1/2 the base, which is 6, times the height, which is 2. No big deal. That's going to be what? I don't know, 65. Now, around y equals 0 is unfortunately a little hard. We actually do have to find the center of this triangle. I think there's a formula for the center of a triangle. I don't actually remember it. I'm pretty sure the center of a triangle is, if you've got something like this, it's 1/3 the height of the triangle. So I'm pretty sure that the center there, I'm like 90% sure. The center there is going to be at the point, the center is the point 3, 1/3 of the way up. Well, 1/3 of a height of 2 is 2/3. So 2 plus 2/3 is 8/3. I'm pretty sure that's where my centroid is, but I don't actually know. So what am I going to do? Well, I'm going to find the moment. So how do we find the moment of this? Well, we already have the mass, right? Or the area, I should say, right? The area of that triangle is 1/2 times x times 2, which is 6. And the moment around the x-axis. So we're going to have to do it in two parts because there's two different functions here. So it's going to be the moment of this region plus the moment of this region, which probably should be symmetrical. So let's see here. I suppose we really could do it the moment of this region divided by 3, because this triangle has an area 3, and this triangle should have the same like height. So if we'll do it as one piece, but let me just show you. So let's see, this line here, the equation of that line, well, let's see. I know I have a y-intercept of 2, and I know my slope, I'm going over 3 and up 2, so my slope is 2/3. Okay, so then if I want to find the moment of this region around the x-axis, I'm going to use the terrible formula, I guess. So let's see, the terrible formula would be, I really want to use the terrible formula? Yeah, I guess I can do it. So the terrible formula would be that the moment around the x-axis is 1/2 the integral from 0 to 3 of this function squared minus the bottom function, which is y equals 2 squared. So it'd be 2/3 x plus 2 squared minus 2 x. Not the funnest thing ever, but it's fine. It's gonna be 1/2 integral from 0 to 3. Squaring this out, you get 4/9 x squared plus 2/3 times 2, which is 4/3 times another 2, which is 8/3 x plus 4 minus 4 cancels out. So then integrating this, you get 4x cubed over 27 plus 8x squared over 6, all times 1/2 from 0 to 2. So distributing the, plugging in, I guess, let's distribute the 1/2. You get 2x cubed over 27 plus 4x squared over 6 from 0 to 2. So that's going to give me 8/27 plus 4 times 4 is 16/6. That's really 8/3. So you've got 8/27 plus 8/3 times 3 over 3 is going to be 24/27. So you're going to get 32/27. Which is not what I thought it was going to be, which is fine. Yeah. And so, assuming I didn't make a mistake, which is totally possible, let's double check. Let me just see real quick here. I went over 3 up to 2/3 x plus 2. That's right. Okay, the plug in 3 against. Cool. 4/9 x squared plus 8x. Yep, cool. Okay, okay. This is going to be 4x cubed over 27 plus 8x squared over 6. Oh, I did make a mistake. 2 times 2 cubed is 16. So this is an example of why it's good to have maybe expectations about what things should be. I already had an idea of what I thought this should be, and when it didn't come out that way, I was like, I should maybe go back and look. So this is really 16/27 plus 8/3, which still probably isn't going to come out with what I thought it was going to be, but that's fine. But I did do this math wrong over here too, making all kinds of mistakes. 16/27 plus 8/3, 8/3 times 9/9 is 72/27. And that's going to be 88/27, which is still not, that's it's close, but not exactly what I want. Again, assuming no mistakes. Yeah.
James,
Yes.
a quick question. How come like when we start, how come you square everything like 2/3 x plus 2?
Because I'm using the formula that if you have functions of x, the moment they're on the x-axis is 1/2 the integral of f squared minus g squared dx. Right, I'm taking the shortcut. Oh, thank you. Yes, Hannah. Sorry, I didn't mean to call it, but someone pointed out that they found my other boo-boo. But let me answer the question that was asked first. So, right, we're just using, right, it's really the integral of 1/2 f plus g times f minus g dx. F minus g dx is the area of our rectangle, and 1/2 f plus g is how far it is from the axis of rotation, or a lever arm.
Mhm.
But yeah, so that's, but then we simplify that and we get this. So that's why we're getting 1/2 the function squared minus the function squared.
Okay.
But yeah, I mean, thank you for the correction there. I made a mistake. That 3 somehow magically transformed into a 2, which it's not. Okay, there's still a chance it could be right about what this is supposed to be. So this would be 0 to 3, which is actually going to come out much nicer. So now when we plug in 3, we get 2 times 27 over 27, awesome, plus 4 times 9 over 6. Those cancel. This is 2 and a 2 cancel, and then a 9 and a 3 cancel. That seems very wrong. Let me, sorry, I feel like this is what happens when you make up problems on the fly. Sometimes things get really kind of messed up. Yeah, that seems right though. Let's see. 4x cubed over 27, 8x squared over 6. Just make that a 4/3 instead of 4. Oh yeah, no, that's fine. I'm sorry. Yeah, that comes out just right. So that's 2. So we get 2 plus 6, which is 8. And then the moment divided by the mass, which again, the mass of, or the area of this half of the rectangle is 3, you get 8/3. And then in a similar way, the moment of this would be exactly the same, right? It's the same sort of region, right? By symmetry, you can say the moment of this is also 8, divided by its area is 8/3. So yes, the center of a rectangle is, if you've got a rectangle, is like this line that's 1/3 of the height away from the bottom is always going to cut the area in half, which is kind of cool. And then we can answer the question, what's the volume of this shape revolved around the x-axis? The volume would be 2 pi times the distance from the center of mass, or the centroid, which is 8/3, times the area, which is again 6. Kind of cool. Yeah, really kind of cool. Which I guess is kind of interesting, right? This 8/3 times 6 is just the moment of the whole shape, right? The moment here was 8, the moment here was 8, the total moment is 16. 8/3 times 6 is 16. That's kind of interesting. I guess it only works if you're going on the axis of interest. But actually what's kind of cool is that Papps's theorem can show up in other places as well. Basically, the idea of Papps's theorem is that if you're working with the region that you're doing something to, you can kind of always think of all of the stuff of that shape, whether it's an area or something else, as centered at the center of mass. So for example, with fluid force, so let's say we have, like, for example, some thin plate that's sitting vertically. It's got a height of 2 feet. It's got a width of 4 feet. And it's in a 10 feet deep pool. And I want to find the fluid force due to pressure on the plate. So one way to calculate this would be draw a little strip. Say, okay, that strip is at a depth of 10 minus y. Sorry, right? This is at y. This is 10 minus y. So the fluid force is the integral of the depth times the area, which is 4 times dy. And then I'm forgetting something. Oh yeah, times the density. Density of whatever it is. I don't really care what it is right now. And that's going to be the integral from 0 to 2. So we're going to get 4 delta times integrate 10 minus y, you get 10y minus y squared over 2, 0 to 2. You plug that in, you get 4 delta times 20 minus 4 over 2 is 2. So you get 4 times 18, which is going to be 72 delta. Or you could say, what if all of that mass was just right there at the centroid of the rectangle? Well, then we can say, well, all that mass is at the depth of 9 feet. Right? If it's just right here, that's 2 feet. Well, the center of mass is exactly, right? If it's a rectangle, the center and the density is constant. The center of mass is just at the center of the shape. So that mass there has the force on it's going to be, again, the density times the depth of the centroid times the area of the rectangle. Again, right, that's 4. So that's going to be your density. The depth of the centroid is going to be at 9. And the area of the rectangle is 4 times 2, which is 8. 72 delta. Kind of neat. So Pappus's theorem kind of is applicable in other ways. Sure. Let me do one more because I didn't address the one question that was actually asked. So let me do one that's kind of like it, and then we'll move on to maybe some U sub, but definitely some. I mean, I guess it's in there. Some differential equations.
James.
Yeah.
Could you quickly flip back the light for a quick sec? Okay, thank you, James.
So what if we had a shape with whose coordinates were at, say, I don't know, like, let's say at 1, 4 and at 4, 1 and also at 4, 7 and at 7, 4. What kind of shape would we have?
Square.
Right, definitely a square. All these are kind of spaced out in a very equal way. So I want to find the volume we get when we revolve around, I don't really care what we pick, actually. Let's pick something crazy like y equals 9. Okay. Pappus's theorem, right? We definitely don't want to find the centroid of this hard. We don't have to. The centroid of a square is the literal center of the square. So you can find the center of the square by just seeing where the diagonals intersect. So the center of the square has got to be right there. This vertical line is the line x equals 4. This horizontal line is the line y equals 4. So the centroid is at the point 4, 4. Great. What's the area of the square? That's a slightly maybe harder question to answer. So we need to find the length of a side here. So I'm just going to use the distance formula, right? The distance from 4, 1 to 7, 4. The distance is going to be the square root of 7 minus 4 squared plus 4 minus 1 squared, which is the square root of, let's see, 7 minus 4 is 3, squared is 9. 4 minus 1 is 3, squared is 9. So that's going to be the square root of 18, which means the area of the square is the square root of 18 squared, which is 18. So then the volume is 2 pi times the length times the area. The length from our centroid to our axis of rotation, y equals 9, is going to be 5. The area of our square is 18. That's it. So when they ask you something kind of wacky like this, where they're like, find the volume of this kind of shape, that'd be hard to do, like using the disc or the washer or the shell method. The intention is you're supposed to be able to relatively easily find the centroid of that shape and then use Pappus's theorem. That's definitely the gist of a problem like that. Okay, let's see. Oh yeah. So there's something I failed to mention, which is fine. We'll talk about it now. So there's this kind of weird little section 7.1, I think, where we talk about the definition of natural log of x being an integral, which is kind of funky, but I mean it works. So let me show you one example of this. So yeah. So I'm going to say that the natural log of x is equal to the integral from 1 to x of 1 over t dt. And it is. So right, it kind of looks like this. So here's 1, here's t. Here's my 1 over x function. And this area here right, that area is equal to the natural log of, oh, sorry, from 1 to x, not from 1 to t, sorry. That area is equal to the natural log of x. Great, so what can you do with this? Well, you can prove some rules about logarithms. For example, we could prove using this that the natural log of x times y is equal to the natural log of x plus the natural log of y. Seems kind of crazy, but let's work on it. So I'm going to start with the natural log of x times y. So I'm just going to replace x with x times y. So I'm going to say that the integral, I'm actually going to start with the natural log, right? So the natural log of x times y equals the integral from 1 to x times y of 1 over t dt. Okay, so then we're going to do a u substitution. So I'm going to say, right, that this is equal to 1, it's equal to xy. And I have to think about this for just a minute. So I want yeah, that's funky. So I want, let's see, what do I want to do here? Yeah. Sometimes they'll tell you how to do the u substitution. Let me take a look here. So I want u to equal, and what I really want to happen is for this upper limit to change into just to change into x. That seems interesting. Okay, here's what I'm gonna do. I'm gonna let, okay, actually, I'm gonna let u equal t divided by y. I think that's right. Let me double check. These problems are always weird. So that means t equals u times y. Okay. Yeah, that should work out all right. So then dt, oh, also, right, so remember so t is our variable, x and y are just kind of acting like constants. So then our du is going to be 1 over y dt, or y times du is equal to dt. That seem all right? Like, maybe, I don't know, let's find out. So I'm going to rewrite this as, so dt becomes y times du. And 1 over t, what's 1 over t? Well, let's just replace t. T is equal to u times y. So it's going to be 1 over u times y. Oh, great, the y's can cancel. And now if t equals 1, u is going to equal 1 over y. And if t equals xy, u is going to equal xy divided by y, which is x. This is kind of sneaky. So then we have the integral from 1 over y to x of 1 over u du. Okay, so then, oh, this is extra sneaky because, yeah, interesting. The problem here is I want to jump straight to the end, but I can't. I want to say this is equal to 1 over u. I want to just integrate that. Well, so the thing is, I have to write it basically as 2 integrals like this. So I'm going to break this up as, yeah, I'm going to break that up as the integral from 1 to x of 1 over u du minus the integral from sorry, I'm doing that completely bonkers. Integral from 1 over y to 1 of 1 over u du plus the integral from 1 to x of 1 over u. We're just breaking it up at 1. All right, this one, that is the natural log of x. This one we still have to work with. So then we're going to do another u substitution. Am I? No, I can be smarter about this. We can flip this. So this is equal to the negative integral from 1 to y to the negative first 1 over u. And then that's going to be, I feel like I'm going to be cheating a little bit here. This would be equal to the negative natural log of y to the negative first, and I can bring the negative 1 down, which does kind of feel like cheating. So that would be the natural log of y. So I'll be perfectly frank. I don't know if I really get the point of these problems. Like, they're kind of neat, but they're kind of a giant pain in the butt. You can, so usually with a problem like this, they will often tell you what sort of u substitution to do, so that it works out. But yeah, kind of a big pain. Trying to think here if there's something else. No, that's fine. We probably could do more here, but I don't really want to. So if this seemed kind of like, why are we talking about this, James? I would be like, I kind of agree. I don't really know why we're talking about this, but some people like to talk about it. Sometimes they like to make you do things with it. I don't think it's that important. So let's go ahead and move along.
Wait, James, how quick? So like on the right side of the board where you have u equals to t divided by y?
Yes.
Did you like multiply y on both sides, but then divided it once again after you got du?
Well, so I really just looked at this to get my du. But yeah, you can do that as well. Right? You can say the derivative of this is du times y equals dt and then divide the y.
Okay.
Or you could have skipped this completely because I probably just used this really, right?
Yeah.
You could go straight from here to here.
Okay, that makes sense. Thank you, James.
Yeah, it's a little bit of a weird problem. Yeah, that's fine. Okay. So let's look at some. Oh, there was one antiderivative problem that somebody had a question about. So let's look at this one. So let's do the integral of, I'm going to change it just slightly. The integral from 1 to 4. I don't know if I'll do one that was asked. 1 to 2. I don't remember who asked this, but somebody else asked it. 2 to the root x over root x. So the idea here is we want to do a u sub. We're going to let u equal the square root of x. Du, the derivative is 1/2 x to the negative 1/2 times dx. And then I'm going to rewrite this as 2 times du equals 1 over the square root of x times dx. And then I'm going to notice that, oh yeah, I have dx over the square root of x. That's equal to 2 times du. So this integral is going to become the integral of 2 to the u times du. And unfortunately, these limits of integration are a little bit not the best. If x equals 1, u is going to equal the square root of 1, which is 1. And if x equals 2, u is going to equal the square root of 2. So if we're ever asked this, does this look good so far? Anti-differentiating 2 to the u, we get 2 to the u divided by the natural log of 2. And that's kind of just a formula that we're supposed to know at this point. Where it's coming from is the fact that the derivative of 2 to the x equals 2 to the x times the natural log of 2. So if you divide both sides by the natural log of 2, then you have that the derivative of 2 to the x divided by the natural log of 2 is equal to 2 to the x. And if the derivative of something is equal to something else, then the antiderivative of something else is equal to that something. So that's where the antiderivative is coming from. From 1 to the square root of 2. Then we plug in the square root of 2 and we get 2 to the root 2 over natural log of 2 minus 2 to the 1 over natural log of 2. And that's kind of all there is to that problem as far as I can see. So hopefully that answered the questions about this problem. All right. So let's move along to some differential equations. Let's start with some easy ones. Oh, sorry, wait. Yeah. So the idea with a differential equation is you're trying to find a function that's a solution to the given equation. Here's a very, very popular example that you guys probably already know the answer to. Or you definitely know the answer, you might just not know you know the answer. So the differential equation, let's say dy dx equal to e to the 3x. That's not quite what I want. That's not at all what I want. I'm trying to write the answer. Is equal to 3 times y. That's what I want. So I'm looking for the function y as a function of x is what? Well, you might know the answer to this already because you've definitely seen functions whose derivatives are equal to 3 times themselves. And I already wrote the answer, I just erased it. The answer here is that y is equal to c times e to the 3x. Because the derivative of y is c times e to the 3x times 3, which is exactly 3 times y. But the question is actually not what the answer is. Well, let's go to the answer. How do we find the answer? I just like, we've seen this one before. You maybe didn't see this differential equation in 21A, but you definitely talked about the exponential growth and decay model. And it is the solution to this differential equation where the rate of change of y is 3 times how much y there is, where the rate of change is proportional to the population size. Very common example. But the question remains, how do we find y of x? Well, most of the examples in this class are either going to be this first type, which is called separation of variables. So when I'm trying to solve something like dy dx is equal to 3y, here's what we're going to do. Look at whatever side your derivative is on. My derivative is on the left. Usually it's going to be on the left, but not always. The thing that's on top, the variable that's on top, that variable and all the variables like it need to go on that side. So in this equation, all the y's should end up on the left. All the x's should end up on the right. Now here's what I can't do. I can't subtract 3y. I can't subtract anything. I'm not allowed to. The only thing I'm allowed to do is to multiply or divide. So I'm going to multiply both sides by dx. I'm going to divide both sides by y. So now I have something I can work with because I have all the y's on one side and all the x's on the other side. It always needs to be true that the differential dy and dx are not in the denominator. That's why I need to bring the dx up over to the other side and multiply by it. It would be very, very wrong to say that my differential equation was 1 over dx equal to 3y divided by dy. That would not work out well for me. So then we're going to integrate both sides. This is called separation of variables. We separated the y's from the x's, and now we're just anti-differentiating both sides. The integral of 1 over y dy is the natural log of the absolute value of y. The integral of 3 dx is 3x. Now, here's what we have. We have plus c1 here and plus c2 here. What I'm really going to do is I'm going to subtract c1 over here and say that I've got plus c2 minus c1, which is really just another constant, which I'm going to call c. Which is why we don't write c's on both sides. Okay, now we're going to solve for y. So we're going to exponentiate both sides. We're going to get the absolute. We're going to get e to the natural log of the absolute y equal to e to the 3x plus c. So e to the natural log of the absolute value of y is just the absolute value of y. And it's going to equal e to the 3x times e to the c. E to the c is also a constant. I'm going to call it a. Yeah. Let's see. So now I've got the absolute value of y equals, I'm going to call e to the c for it. So e to the c times e to the 3x. And then if the absolute value of y is equal to something, that means y can either be plus or minus it. So y could be positive e to the c times e to the 3x, or y could be negative e to the c times e to the 3x. And then what we're going to do is we're going to say that this constant here, it's plus or minus e to the c, whatever that is. It's either one or the other, though it's not both. I'm just going to call that a. Or you can call it c, it doesn't really matter. But look, there's our solution. y equals a times e to the 3x, a constant times e to the 3x, just like we said it was going to be. So, a couple things when solving differential equations. Separate variables. Whatever is on top of your derivative stays on the side it's on. Whatever variable is on the bottom of your derivative goes to the other side. And two, when you're integrating 1 over y and getting the natural log of the absolute value of y, don't sweat the absolute value. Almost all the time, you take care of it when you get to the end, meaning you can just not write it the whole time and it'll still work out just fine when you get to the end part. It's taken me a number of years to really convince myself of that, but it is true that you kind of just ignore the absolute value and it'll all work out in the end.
James, where did the a come from again?
I just called, so I'm saying that a is a new name for the constant that is either positive or negative e to the c.
Oh, okay. I'll write that down. Thank you.
You're welcome. So let's look at some more examples. Let me actually grab some more examples here. Yeah. Where did I leave my examples? Yeah, not you. Yeah, not you either. Sure, let's try that. So let's say we have the following differential equation. dy dx equals 3x squared times e to the negative 4y. And I want to solve this differential equation. Okay. So I'm going to bring all my y's to the left, all my x's to the right. So I'm going to have dy divided by e to the negative 4y equals to 3x squared times dx. Great, let's say I differentiate those sides. So I'm going to rewrite this as the integral of e to the 4y times dy. The integral of 3x squared is just x cubed. Let's see. The integral of e to the 4y is e to the 4y divided by 4. Still equals x cubed plus c. Let's solve for y. So you're going to get e to the 4y equals 4x cubed. You could write 4 times c, but 4 times a constant is just a constant. So I'm going to call this c. If you really don't like that, you can say, okay, this is c1. And then when I add c, a constant to it, or when I multiply by 4, it becomes a new constant c2, if you really like. And then solving for y, I get the natural log of e to the 4y equals the natural log of 4x cubed plus my constant. And then 4y equals the natural log of 4x cubed plus my constant. And then finally, y is equal to 1/4 natural log of 4x cubed plus my constant. That's it. That's my answer. And if you took the derivative of this, it would equal 3x squared times e to the negative 4 times that. So whatever the derivative of this is, right? So the derivative of all that is equal to 3x squared times e to the negative 4 times all of that. We're not going to show that. We don't need to show that, but it is true. Let's look at another example. Let's see, I've got here, sure. How do I want to write this? Sure. Let's say I've got dy dx equal to y times the natural log of y divided by 1 plus x squared, with the initial condition that y of 0 is equal to 1 plus x squared. 1 plus x squared. E squared, sorry. All right, same process. We're going to bring the y's to the left and the x's to the right. So I'm going to get, I can divide by y natural log of y. So I'll have 1 over y natural log of y dy equals 1 over 1 plus x squared dx. And then we're going to integrate both sides. The integral on the right side maybe isn't easy, but it is straightforward if you know it. This is just the inverse tangent or the arc tangent of x. This one, on the other hand, does require a u substitution. So for this one, we're going to let u equal the natural log of y. And then the derivative du is 1 over y dy. I exactly have that. Right, there's my du. There's my du, which is 1 over y times dy. So this integral becomes the integral of du over the natural log of y, which is u, which is the integral of 1 over u, which is the natural log of the absolute value of u, which is then the natural log of the absolute value of the natural log of y. So here's what we have. We have that the natural log of the natural log of y is equal to the arc tangent of x plus c. I did drop the absolute value. That was on purpose because I know it's going to work out fine in the end. So I'm going to exponentiate both sides. So e to the natural log of some stuff is the natural log of y, right? It's stuff equals e to the arc tangent of x plus c. And then finally, doing it again, e to the natural log of y is going to equal e to the arctangent of x plus c. That's going to be y equals e to the arctangent of x plus c. Okay, and now we want to find, so we're given an initial condition, which means we should be able to figure out what that constant c is. So if I plug in 0 for x and 2 and e squared for y, I should get e squared equal to e to the arc tangent of 0 plus c. Okay, it looks a little crazy. What's the arctangent of 0? Oh, what is the arctangent of 0? 0. So basically, I'm just going to get rid of the e's here and say, well, 2, the exponent here has to equal the exponent here, which is e to the arctangent of 0 plus c. But arctangent of 0 is 0, so 2 has to equal e to the c, so c has to equal the natural log of 2. And then we're not done yet. We have to go back and write that our final answer is y is equal to e to the arctangent of x plus the natural log of 2. Kind of bonkers. Actually, it's not really that bonkers. It just feels like a weird answer, but it's really not that. Sorry.
James. So where sorry, where was it again that you decided to plug in our initial condition?
So I waited till the end, like till I'd solve for y as a function of x. But sometimes you're going to see that there are more convenient places to plug it in. They're probably you might so it might have been more convenient to plug it in at the very beginning. Let's go back and take a look. So that's a good point. sometimes the problem with doing it at the beginning is then you have to kind of carry that with you the whole way when you solve it. If I had gone back to the natural log of y equal to the arc tangent of x plus c, and I plug in e squared for y and 0 for x, the natural log of e squared is 2. So I have the natural log of 2. And arc tangent of x, arc tangent of 0 is 0. So you get c equal to the natural log of 2. So you could have had that there and then just carried it the whole way through to get the final answer here. So it really doesn't matter. Well, it matters a little when you decide to use your initial condition to find your c. Usually, it depends. It really depends. It depends on what your initial condition is, and it depends on what kind of differential equation you have.
That makes sense. Thank you, James.
Oh. So let's say we had something like the following. Where'd you go? Yeah, we have this word problem here that someone sent me that I should definitely look at. Let's say we have dy dt is equal to 2 times y minus 80. And if y is equal to 30 at t equals 0. So we want to solve this with this initial condition. Now, something to be really aware of. You could write this as dy dt equals 2y minus 160. There's no reason to do this, but you could. But here's what you can't do. You can't add or subtract. So the only way to get y down to the denominator over there is to divide. To divide either by 2y minus 160, or preferably divide both sides by y minus 80. So that we have dy divided by y minus 80 equal to 2 times dt. And then we're going to integrate both sides. So then we're going to get the natural log of, I'm going to not write the absolute value, even though there should be one there. Natural log of y minus 80 equal to the integral of 2, which is 2t plus c. Now I'm going to do the exponent of both sides. So I'm going to do e to the natural log of y minus 80 equals e to the 2t times e to the c. And then I've got y minus 80 equals this constant a, which can be positive or negative because there really was an absolute value there, times e to the 2t. Right, I'm calling this a. A is really plus or minus e to the c. Okay, so then we can probably just plug in it probably makes sense to plug in right now. If I plug in y equals 30 and t equals 0, I get 30 minus 50 equal, 30 minus 80 equal to a e to the 2t. So then negative 50 equals a equal a e to the 2 times 0. Okay. So then negative 50 equals a times e to the 0. So negative 50 equals a. So then my solution is y equal to 80 minus 50 e to the 2t. The initial condition is right. If you plug in t equals 0, you're going to get y equals 30. And the derivative is also right. If you take the derivative of this, you're going to get 2 times this minus 80. Yeah, that totally makes sense, right? If you take the derivative, so let's check this one because it's pretty easy to check. So dy dt is equal to the derivative of that, which is 0 minus 50 times e to the 2t times 2. So it's equal to negative 100 e to the 2t. And 2 times y minus 80 is equal to, well, y minus 80, the 80s cancel, and you get 2 times negative 50 e to the 2t, which is exactly equal to that. Totally works. Cool. Okay, let's look at this word problem. I'm gonna erase the other side actually. So a lot of differential equations problems are gonna, maybe not a lot, but certainly some of them are gonna be presented as a word problem where something is changing as a function of what the thing is. Like this next example, which is, I don't know which problem this is. It's the oil problem from your homework. Let me use my numbers here. So, my eyes are tired. So, oil is pumped continuously from a well at a rate proportional to the amount of oil left in the well. So, you got a well. There's oil in it. And we're pumping that oil. So let's say that dP dt is the rate we are pumping the oil. Let's use dq dt, which is q for the quantity of oil. So q of t is the quantity of oil, and dq dt is the rate of change. It's the rate of change of the oil, which means, right, it's how fast the oil is being pumped at. It's how fast we're removing the oil. It's the rate of change of the amount of oil. But it's presented as a positive number, right? If you said what's the rate of change of the amount of oil, it'd be a negative number because you're losing oil. But if you talk about the rate you're pumping the oil at, it's a positive number because you're just saying how fast are we moving the oil. So, and here's what they're telling us. They're telling us that oil is pumped continuously from a well at a rate that is proportional to the amount of oil left in the well. So dq dt, the rate we're pumping at, is some constant times the amount of oil we have. The more oil we have, the faster we're pumping it. And as the oil reserves dwindle, we're going to pump it more slowly because the rate we're pumping at is proportional to how much we have. Okay. And then what else do we have here? And then we have some initial conditions. So at initially, so time equals 0, there were 3 million barrels. So Q is 3 million barrels. And then sometime later, 6 years later, the amount of barrels is half of that. It's 1.5 million. Okay. At what rate was the amount of oil in the well decreasing when there were 1.8 million barrels remaining? So they're asking us, so here, let me read the words again. You guys should listen. At what rate was the amount of oil in the well decreasing when there were 1.8 million barrels remaining? So they want to know the rate, which they've written in as barrels per year. And they're asking for that when there were 1.8 million barrels remaining. So that's when Q is equal to 1.8 million. Okay. So we need to do some stuff, right? All we have is this so far. Now here's the good thing about this. We know the solution to this differential equation. Whenever you have a differential equation where the derivative is equal to a constant times that, okay, what do they call it? There's a name for it. I mean, it's the exponential growth model. I feel like there's another name for it. But that's what we've got. We've got the Q of t has to equal some e to the kt times a constant. That's it. But I do think that's worthwhile to think about it this way. So then I want to figure out what k is. So I'm going to say, well, when I plug in t equal to 0, q is going to be 3 million. All right, 3n. I can write some zeros. So that means C is going to be 3 million. And then when I plug in time equal to 6, I'm going to get Q equal to 1.5 million. So that means 1.5 million equals 3 million. That's our C value times e to the ket. We can solve for k. Divide both sides by 3 million, you get 1/2 equals e to the k times 6. Sorry, I forgot to plug in that 6 for t there. And then take the natural log of both sides. Natural log of e to the k times 6 is just k times 6. Divide by 6. So k is the natural log of 1/2 divided by 6. And now here's the thing. Normally, when we were solving something like this, like in 21A, when you're doing exponential growth and decay, you would plug this back into your model, and you would answer some questions about like how much stuff there is at a certain time, or how long does it take until there's so many barrels left. But the question they're asking here is, what is the rate of change when there are 180 million barrels left? Well, that there is your rate of change. So we actually have to plug in k equal to the natural log of 1/2 divided by 6 and q equal to 1.8 million. So it's actually pretty easy to calculate. The rate of change when there's 1.8 million barrels left, dq dt, is going to be k, which is the natural log of 1/2 divided by 6, times q, which is 1.8 million barrels. And you can simplify this if you wanted to 300,000 times the natural log of 1/2 barrels per year. That's how you calculate that. Let's do a couple more. Maybe one more. I got one more. So I got some better ones. Yeah. So let's say we've got, what do I have here? X cubed plus 1 times dy dx equals let me think for just a minute here. Sure. Y. Yeah. Sure. Let's do it that way. X squared over come on, brain. X squared over y squared. Let's be careful. Yeah, I think that's it. Yeah. Not quite as exciting as I wanted to be, but that's all right. So let's say we've got this. So we're definitely bringing our y's to the left and our x's to the right. So we're going to have y squared times dy equals x squared divided by x cubed plus 1 dx. Let's integrate this thing. So integral of y squared is y cubed over 3. The integral of x squared over x plus 1, we need to do a little bit of work. Our u is going to be x cubed plus 1. Our du is going to be 3x squared dx. So 1/3 du is equal to x squared dx. So this is going to be the integral of 1/3 du. Now, it might seem very tempting to cancel the 3's here, but I wouldn't recommend doing that until we've at least done one more step, or 2 more steps, until we've integrated this really. Although it's probably safe to cancel them, I just don't want to make any mistakes. So integrating this, we get 1/3 the natural log of the absolute value of u plus c. And then we have y cubed over 3 equals 1/3 the natural log of x cubed plus 1, an absolute value, plus c. And now it seems like it's pretty safe to multiply both sides by 3. So multiply both sides by 3, you get y cubed equal to the natural log of the absolute value of x cubed plus 1 plus 3c, which is just a new constant. And then finally take the cube root of both sides. And there we go. So solving separable differential equations isn't too bad. It really is just a process of bringing all of your things on top to that side it's on and things on the bottom to the other side it's on. I usually say it's almost always written as dy dx on the left. So we're almost always bringing y's to the left and dx to the right, or y's to the left and whatever's on the bottom to the right.
James, I have a good question.
Yeah.
But this is one small thing. It's for the u substitution part. When do you know which u to pick? Because I know this, we picked the bottom part because it had the highest exponent, right? But
Well, I picked the bottom part really because its derivative is also in the integral. What's the derivative of x cubed plus 1?
X squared.
Right, and I have an x squared.
Okay, so like say we're doing just a problem, it's pretty much where it's convenient to cancel stuff out.
Right. So let me give you another example. Sorry. Let's give another example. Sure. Let's say we have this. Let's say we have sure, fine. E to the y times dy dx equals e to the y x. That's always a good y plus times x plus 3y. Okay. Is that going to work? It's not going to work. Sorry. I meant to do plus 3x. There we go. That's going to work. Okay. So I want to separate my variables. So I want how do I separate those variables? I mean, I've got e to the y times dy equals e to the y times x plus 3x times dx, but I need to move that y over to the left. What can I do? I can factor. I can write that as e to the y dy equals x times e to the y plus 3 dy. And then I can divide by this and say that e to the y divided by e to the y plus 3 dy equals x, sorry, for dx. And so here, again, we're going to need to do a u sub. And the choice for u, I want to pick u to be e to the y plus 3. 1, because it is in the denominator, but 2, because its derivative, du dy, is equal to e to the y. And I exactly have that right there. So that du is equal to e to the y dy. So that this becomes the integral of du over u equal to that which is x squared over 2 plus c. The integral of du over u is the natural log of the absolute value of u equal to x squared over 2 plus c. But u is equal to e to the y plus 3. So I have the natural log of, I don't need the absolute values anymore usually, but especially here because e to the y plus 3 is already positive. And let's say that we're given the initial condition as well, that I don't know, that y of, I'm gonna make that something probably stupid, y of 1 was equal to 0. Now I want to solve for c. It might make some sense to solve for c right now. So I plug in 1 for x and 0 for y, I get the natural log of e to the 0, which is 1 plus 3, which is 4, equal to x squared over 2, which is 1 over 2. So my c value would be kind of gross. It's the natural log of 4 minus 1/2. And then solving for y, so I'm going to e both sides. So I'm going to have e to the natural log of e to the y plus 3 equals e to the x squared over 2 plus c. I'll fill in the c a little bit later. Then e to the natural log of stuff is just stuff. So I get e to the y plus 3 equals e to the x squared over 2 times e to the c. Subtract 3. Take the natural log of both sides. So that y equals the natural log of e to the x squared over 2 times e to the natural log of 4 minus 1/2 minus 3. Kind of gross.